Okay, welcome to this Wednesday's lecture. It's our last lecture for energy, so we're going to follow up our discussion of what we did yesterday. Now, before we go too much further into our energy discussions, I just wanted to briefly mention some things about the midterm. So, your midterm is this Saturday. For many of you, it's going to be from 8 a.m. to 10 a.m. Eastern Standard Time. And if you are east of Toronto, this is not a problem for you because as you travel east, you get later and later in the day. So, if you're in Europe, you're 6 hours ahead, for instance. So, it wouldn't be 8 a.m. for you. It would be kind of mid-afternoon for you. And if you're over even farther east, like let's say over in Asia, you would be, it might be in the evening for you. It might be 8 p.m. Maybe depending where you are in Asia, it might be like 9 p.m. for you. Again, most people are awake in and around 9 p.m. It's not unreasonable to assume people are up and ready to take a test at 9, at least for one day. However, people west of Toronto, like maybe not, well, I don't think there's anyone in Manitoba, but Calgary, or anywhere in Alberta, I should say, anywhere in BC. If you've identified in the survey that you are west of Toronto, I have gone in and I've adjusted your start time to be reasonable. I agree that I do not think it's reasonable for, to expect students to wake up at 5 a.m. to take a test. If you're, for instance, west of Toronto. But if you're east of Toronto, expecting students to take a test, mid-afternoon or, evening, I think that's pretty standard. It's not an unreasonable time. But you'll notice that if you go click on midterm 1, now that I've mentioned it, a bunch of you were able to do it. If you click on midterm 1, it should say this assignment is locked and will become available to you on May 23rd at 8 a.m. But for those of you west of Toronto, you'll notice that it says a different time. It'll say something like it'll become available. Let's say you're in British Columbia and you're 3 hours behind us. It'll say something like this quiz will become available May 23rd at 11 a.m. So 11 a.m. Toronto time, I think it's 8 a.m. your time. So that way you're kind of on par with everyone else. The same expectations of students locally would apply to you over out west. So I hope that's equitable, and I hope everyone thinks that's fair. It's trying to schedule people around the world to take a test mostly at the same time is quite difficult. So I hope we can accommodate people as much as humanly possible. I will also remind students that it is their responsibility to have read the midterm blurb ahead of time under the midterm 2020 info page on Canvas. A lot of important information there, and if you want to wait until the day of the midterm to read it, I mean, that's fine if you want to eat into your time on the midterm. So I didn't want to force you to eat into time on the midterm, so I did post the sort of blurb ahead of time. The gist of it pretty much says, please be an honest and reasonable human being. It lists the aids that you're allowed, standard things are allowed. It lists the material that's covered, so I don't get a bajillion emails asking me the same thing. It also talks about a little bit academic honesty and integrity, things like, a midterm is supposed to evaluate your own knowledge and individual amounts of knowledge, not a collective amount of knowledge. So, we are asking that you refrain from communicating, obviously, and we're reminding you a little bit in that blurb what is considered an academic offense. A lot of people think that, the test is only 2 hours. I can post a question on the discussion board, and by the time the prof finds it, the test will be over and I would have submitted my answer already. Well, that's probably true, but a lot of times students don't know that these discussion boards online, like Chegg, for instance, and Course Hero and Stack Exchange, they actually are forced to comply with academic integrity investigations. So I don't actually have to rack my brain and stress myself out during the test traversing these sites. I can do it at my leisure after the fact. And if I notice any of the questions posted online, all I have to do is go to the office of registrar with the link and the Office of the Registrar will actually launch a formal investigation with the website. And the website is forced to comply with all of the information from the user who posted that question. So it's not like we have to do it live, and as soon as the test ends, like you've gotten away with it. We can definitely go back and do it. And in fact, to make matters even worse for people who try to do this, as long as you're a student at U of T, it doesn't even you could be finished the class. As long as you're still a student at U of T, if we happen to notice a question that was posted during an assessment, let's say 3 years down the line, let's say you're in first year now, you're halfway through your fourth year. If we notice like 3.5 years later that you had posted a question during an online take-home midterm, we can still charge you with an academic offense. So please do not tempt fate. It's much easier for students to just take the test honestly. It's less stress. It's better for everyone if you just kind of give it your good old college honest effort. And then that way it's easier to mark as well, because it'll be your own work. Okay, moving right along here, let us resume with what we left off with yesterday. All right. So we left off with a breakout session. It worked reasonably well. I think it worked better than it did last time we did it in lecture. I don't think we have time today to try a breakout session. So maybe in a future lesson, we might try it once more just to see if students are kind of picking it up more and more. Today, though, we have to forge ahead. So just a little bit of a recap. Yesterday, we introduced the notion of energy. So I'm just going to scroll to the top. As I'm scrolling, can you guys just let Brandon know if the picture is lagging behind my words at all? And if there is, Brandon can unmute himself and let me know. So yesterday, we introduced the idea of energy or the work done on a system. And we motivated this by saying there was a piece of our analysis puzzle that was missing. We started our path in this class with trying to predict motion. Assuming motion already exists, where is the object going to go? That was kinematics. Then we said, okay, well, we're happy with kinematics, assuming we have constant acceleration. However, there's a piece of the puzzle missing, is what caused the motion. So that forced us or led us to develop ideas in dynamics. And, that's where, Newton is given the official credit for that. Newton came in and formalized his 3 laws and the equations of dynamical motion, F net equals ma. And we had this sort of equation here, F net equals ma, I circled it there in black, that relates the new variables in the new chapter, so it relates forces to the old variables in the old type of analysis, acceleration. So that would be the coupling equation between dynamics and kinematics. So now that we have this hole that we've identified, we say, okay, we got to branch out into energy. We now have this new variable, work done, W, or this notion of energy. We need a way to relate the new material, the new chapter, to ideas and concepts in the previous chapter. Now, we don't necessarily have to relate it to dynamics. We could have easily, or not easily, but in theory, the scientific method says there was nothing that forced us to relate it to dynamics. We were just trying to find some sort of link to a previous set of knowledge. And once we can find a road that connects us to a previous chapter, then the pre-existing roadmap that navigates us in between the other existing chapters will allow us to drive in between the different chapters. So it just so happened that the thing that related work, this new idea, to the previous chapter happened to be a road between the city of energy and the city of dynamics and forces. But once you've driven back into forces, then you can go back into dynamics, kinematics if you wanted to. So work equals the dot product between vector force and displacement d. That is the equation that couples this new information. So we did a lot of work on that. And we also, the second equation we did yesterday was something called the work energy theorem. Oh, there it is right there. And this stemmed from the fact that we had F net equals MA, which is the head honcho equation in dynamics. And we had previously been looking at the work done due to a singular specific force on a system. So the work done by friction, or the work done by the tension, or the work done by the applied force, or the work done by gravity, right? These are the work done by an individual force. F net equals MA is a way to sort of say, well, what's the net force on the object, and how would this net force impact the causing of motion, which would be the acceleration. So we can actually use F net equals MA and calculate the net amount of work done on the object, not just the individual work from the individual forces, but the net amount of work. So we started with, in black here, let me just change my pen color. In black here, we had F net equals MA, and then in red, we took the dot product with the displacement, and using the definition of energy, we were then able to say F dot D is equal to work done. And it's the work done due to the force F. In this case, the force F is the net force, so it's the net amount of work. And then the right-hand side is just the right-hand side. And then we used the kinematics equation to obtain a sort of rearrangement of what we were doing. And we were able to determine that if the left side had units of joules, then each individual term on the right-hand side also needed to have a unit of joule, which means that each term represents a type of energy. And physicists were nothing if not pragmatic. I know it may not seem like we're pragmatic when you're doing homework and listening to lectures, but trust me, we are very pragmatic. And when we're trying to name something new, we were looking at this on the right-hand side here, and we were saying, okay, well, we know that this is some sort of energy because it needs to have the unit of joule. What should we name it? Should we call it like Mark's energy? No. You know, physicists noticed that it was dependent on velocity, motion. And back in the olden times, I mean, we named kinematics to be the study of motion, you know, the trajectory. So we call this kinetic energy. It's the energy associated with motion. So yeah, just to recap from last lecture, we formalized the notion of kinetic energy. And we said that the net amount of work done on a system can be measured simply by looking at its change in kinetic energy, which is actually quite profound. We also did a bunch of questions to practice those ideas yesterday as well. So now we can actually move on to the juicy details of this chapter and finish off energy. Hopefully we finish it in the remaining hour and a half. So I motivated this whole topic that physicists needed to develop energy. We didn't just want to, we needed to, because we were unable to, literally unable to, analyze objects that did not have a constant acceleration, right? In kinematics, we assumed A was constant. Whether it be a subway accelerating, or a subway car accelerating with a certain acceleration of, let's say, like 2 meters per second squared, or if it was dropping an object off a building and it accelerated at 9.8 meters per second squared. Either way, we assumed it had a constant acceleration. However, very few things in life have constant acceleration. So there was a big missing gap here. And now that we've done all the legwork, we've kind of introduced the idea of what a joule is and how it's a scalar, and you know, what is work? How does a force interact with the system? It's F dot D, right? Now that we've done all that legwork, now we can go back and we can kind of see and delve deeper into these concepts to see how does this solve our puzzle piece problem. So let's do that now. I'm claiming that energy is the solution to analyzing a variable force. So let's go straight into it, shall we? One way to think of what's about to happen is with a graph. Now, not all physicists would choose to teach it this way, because physicists themselves would not necessarily think of the problem in this fashion. But I think, seeing as how I know where you guys are coming from, many of you are coming from first year calculus, many of you have already taken first year calculus maybe a few years ago, and even if you hadn't, you've at least taken some sort of math in high school. So I'm going to try to relate this new piece of knowledge back to what you've learned in basic math. And hopefully this becomes, you know, it gives you a method to think about it and put it in your head in a logical way. So we were shown yesterday that the work done is FD. And let's just for a second assume that oh, I'm still on pointer mode. Okay, the work is FD. And let's just assume for a second that F is parallel to D, just to make our construct a little bit easier to understand. I don't want to confuse you and add too many layers all at once. What we can do here is we can plot a graph. Let's say this is the X position, and let's say this is the force axis. So it's a standard XY plane, but instead of labeling it XY, I'm going to label it force as a function of location. Well, if I draw a horizontal line, as we see kind of here, this tells me that I have applied the exact same magnitude of force to this object as the object moves forward, right? As the object moves forward either across the floor or as it's spinning or the car is driving. If the force versus position graph is a horizontal line, this means the force is constant with time. So let me just choose red here. This means the force is constant. Now, if the force is constant, we also know from F net equals ma, if the force is constant, A is constant. And then we're back in the old realm that we assumed you know, A was constant and everything's hunky-dory. So the first graph here that I'm showing you is actually not the problem. We know how to analyze this graph, not a problem. So I'm starting with basics in this new way of thinking about this, just so you can kind of connect it to the new ideas here. However, look at this equation here. Work is equal to the product of the force multiplied by the displacement. Well, force multiplied by displacement is simply the area under the curve, right? This distance here is the force. This distance here is the displacement. If you multiply those two quantities together, you simply get the area of that rectangle, or more specifically, the area under the graph. Now, the graph on the right-hand side of the yellow arrow here is a graph that I've taken from the Stewart calculus book. Full disclosure, I obviously didn't make it myself. I took this graph out of the Riemann sums chapter of the Stewart calculus book. And really the idea I want to drive home here is, and I think we might need a little bit more space, so let me just insert some space here. Okay, really the idea I want to drive home here is work done. The work done is actually the area under the force versus position graph. Now, in the event force is constant, this is dead easy. You just multiply force times displacement. However, if your force versus position graph is for some reason not constant, which there's many reasons why it won't be constant, because most things in real life do not have a constant force, finding the area under the curve is not as simple as just force times displacement, right? If you did force times displacement, well, you know, let's say this is force, and let's say this is your displacement here. Force times displacement would get you an inaccurate value of the total amount of work done, right? Because it's not a constant force. So the way in which you actually have to do this is you have to do the Riemann sum. And if you haven't taken first year calculus, those words will be meaningless to you. Now, I will remind students this is not a calculus-based physics class. So will you be expected to do calculus on assignments or tests? No. I am showing you kind of where the idea comes from, hoping that you can kind of engage prior knowledge from other courses and kind of tie in information from other disciplines to help you better understand physics. So if you are not taking calculus or haven't taken it, please don't freak out. Just maybe listen to this explanation. Who knows, maybe calculus eventually when you take it will make more sense. Really, the idea behind a Riemann sum is you divide the area under this curve, this non-constant curve, into tiny rectangles. So you say, well, what's the area? If I pick, you know, this x value here, this x value is going to have a certain altitude, right? Maybe this altitude is 150 newtons. And you say, okay, I'm going to approximate. Remember how we opened this class with approximations? I'm going to pretend that over a very small window, let's call this window delta x. Oops, delta x. I'm going to pretend that over a very small window, there's a constant force being applied. Now, I know that's not technically true, but it's over a small interval, so it's an approximation. If you assume the force is constant over a very small window, then you can say this is going to be the force at D1 multiplied by delta x. That's going to be the area of that little rectangle. And then when you move boxes, when you go to the next little box, my writing is too big, so I'm going to skip a box just to accommodate my big writing. When you go to the next box, you're going to have a different y value or a different force value. So maybe this one is 200 newtons. So if I want to know what the work done over this motion, I assume that it's a constant force over that range of x values, which of course it's not technically, but it's an approximation. And if you want to know the amount of work done over this interval, it's just going to be 200 times delta x. And what you would do is you would do that for every single little tiny box that you have within your domain between x1 and x2, or dA and dB. Now, you can choose how big if you remember from calculus, you can choose how big you want these boxes to be. Obviously, the bigger the boxes are, the worse your approximation is going to be. And the smaller your boxes are, the better your approximation is going to be. This is the main idea behind a Riemann sum. And the way you can represent this mathematically is you can say it's going to be the sigma. Now, hopefully you remember what sigma means from math. Oh, you can't really see green on black. There we go. It's the sigma, means the sum from an x value of x1 to an x value of x2 of the force at that location. So this is going to be the force at DI, so like DA or D1, D2, D3, D4, D5, D6, multiplied by the width of that rectangle. So this actually let me take this off. This is actually the work done over interval I. And what you're doing is you're adding up the work done over all the intervals. Now, when you take this width, delta D, and you shrink it so small, your approximation actually becomes precise. And then that's how you turn a summation into an integral. So this is actually the real formula. Formula for work. Now, you see here that the real equation is the integral of f of x dx. In the event oh, I need more space, sorry. I don't know why OneNote doesn't like to add space all the time. Okay, so I'm going to go to black for a second. In the event force as a function of position is constant, we should get back work equals FD, right? Because that's where we started from, work equals FD. So let's see. I'm asserting to you something new. Problem-solving skills. You develop your problem-solving skills when you challenge new information. And when I say challenge new information, I don't necessarily mean berate the source of the of the new information. Like don't berate me, challenging me, and like a lawyer in a court of law. I mean, if you've got questions, by all means ask me. But when I'm saying sharpen your problem-solving skills, I don't mean berate the source of information. I mean challenge the information itself. Test the limits of it. If I'm asserting to you this is the real equation for work done, let's see if in fact this equation can simplify to what we're used to in the previous lecture. And maybe if you can sort of do this in your head and kind of push the boundaries of this new information, it'll better help you understand kind of the concepts behind it. So let's assume in the event that the force is constant, then the work done is going to be the integral between position 1 and position 2 of a constant dx. It's no longer f of x, because f of x assumes that it's a function of x. I'm just assuming force is a constant, so I'm just going to say it's f. Well, force is a constant. You can pull it out of the integral. And the integral of dx is just x from x1 to x2. So this is going to be force times x2 minus x1, which is simply the displacement. So yeah, turns out that the equation I just presented you, it's looking good to be a general case for work done, because if you were to implement the assumptions that we were used to in the previous lecture, we actually get back this same formula we started with. Now you might be thinking to yourself, okay, well, where's the cos theta? If I put cos theta in, well, I could put cos theta into the integral, but in real life, I'll put like a little caveat here. I'll say, oh, that's a terrible N. I'll say note, and then maybe write it in green. Work equals the integral from x1 to x2 of vector f of x dotted with dl. This is vector calculus. Oops. This is vector calculus, and the notion of a DL vector is going to be confusing for you. The notion of having a dot product with an integral sign is going to be confusing to you. So I've chosen to leave out some of the more mathematically rigorous details, given that this is an algebraic-based physics course, and I'm already pushing the boundaries of your math knowledge by showing you the calculus. So before I get a bunch of emails asking me, where's the cos theta, where's the cos theta, I've chosen to omit it just to not confuse you further. Okay, so why am I presenting this to you guys? Now, in the event the video is glitching for you and you want to follow along on your own, I'm in chapter or section 5.1 now of the energy document of the typed notes online. So if it's glitching, you can follow along there. So what do I mean? I've gone through 2 hours of lecture yesterday, 20 minutes this morning, telling you that we need this motivation for non-constant forces, and yet I have yet to even show you a non-constant force. So let's do that right now. So an example of a non-constant force is, say, Hooke's law. Hooke's law, we see, and you've all had experience with Hooke's law because you've had to do the intro assignment, and most of you have taken grade 12 physics, but even if you hadn't, you've at least had to do the intro assignment. You're not missing much, though, if you haven't taken grade 12 physics. All Hooke's law says is that if you have something that is elastic in nature, whether it be a spring, an elastic band, honestly, even like a rubber ball, if you deform the shape of that object, let's say you elongate the spring or you elongate the rubber band, then there is a force associated with elongating or distorting the shape of an object. And this force is to restore that object to its original orientation or its original shape. And the more you distort the object, the more force is pulling it back to where it used to be. So Hooke's law just says force equals minus kx. That's it. K is some sort of constant. You know, there are weak springs, there are tough springs. There's springs in your ballpoint pens when you go clicky, 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 clicky. You can compress that spring with your thumb fairly easily. There are springs in your car for the shocks in your tires, between the tires and the chassis of the car. Those are really, 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 really heavy springs that you know, if you just have the spring in your hand, there's no way you'd be able to compress it, because it's designed to take the weight of thousands of pounds of metal on it. So K is a measure of stiffness of the spring. And X is elongation. You can see here from the picture, as X gets larger, that would mean that there's more elongation or more distortion from its original value. So according to the formula here, as X gets bigger, oh, you can't see green on black. Let me change to red. As X gets bigger, there's more force, obviously. So that's all Hooke's law says. So that's fine and dandy. There's lots of questions in your textbook that involve free body diagrams and forces questions with springs. However, the best we can possibly do is analyzing Hooke's law with dynamics, is finding an instantaneous acceleration for a very specific elongation. Meaning, I could ask you, if I stretch a spring 10 centimeters, what's the acceleration of the block attached to the spring? Well, you can calculate the acceleration for that one very, very, very specific moment in time. As soon as you let go, because there's an acceleration, the spring is going to pull the box inward and reducing the elongation by a few millimeters. And then as soon as you reduce the elongation by a few millimeters, you're changing the amount of force, which means you're changing the acceleration, which means it is accelerating at a slower rate than it was before. And that is exactly the problem. We do not know how to use Newton's second law when you have a changing acceleration. You know, you can use Newton's second law for an instantaneous snapshot in time, but if you're trying to analyze motion, you can't do it with Newton's second law. So how does this help us? Well, we know that the work done is the integral of force dx between position 1 and position 2. So let's see if we can kind of adapt and take what we've learned and modify it to a variable force. So we have a force, Hooke's law, minus kx, minus because it's a restoring force. If you pull it to the right, it pulls back to the left because it wants to go back to where it used to be. So if you plug this in here, you're going to get the integral from position 1 to position 2. Now the force is kx dx, and k is a constant, so we can pull that out of the integral. So you're integrating x dx, and the integral of x is, or the antiderivative of x, is x squared over 2 between x1 and x2. So you can calculate the change in the associated energy using this formula. You can say 1/2 k x2 squared minus 1/2 k x1 squared. And this is going to be the change in the spring energy between position 1 and position 2. If you wanted to know how much energy a spring has, presumably that question, oh, I've just moved down part of what I just wrote. Here, let me just move this back up for you. There we go. If you want to know how much energy a spring has stored in it, you can say, what is the energy stored in a spring from position 0, unstretched, to some sort of stretched position? Kx dx. And this is simply going to be 1/2 k x squared. And there you go. Now, I know, I see the chat buzzing. I bet you any money students are asking me, but Mark, you used x You used X here, and there's a variable X in here. Yeah. Okay, mathematicians, settle down. I know mathematicians are like, yeah, you can't do that. It's the same variable. Okay, pretend they're different. You know, this X here is the iteration variable. It's the variable that I'm changing as I'm integrating, and this is just a final position. So it's a constant. It's not really a variable, but yeah. Nitpicky math. It's okay. This is why mathematicians don't like physicists. We hand wave details all the time. We're still technically right. We drive mathematicians batty. Anyway, so there's the equation right there of for the spring energy. We have previously established the kinetic energy, the energy associated with motion, but we have not necessarily established the energy associated with the spring force. So there's that one. So let's go ahead and do an example, and we'll see kind of how to do this. So this is an example from a previous midterm many moons ago. You can see it's worth 10 points, and it was question 4 on a past test. So in the figure below, a 2 kilogram package slides along a floor with an initial speed of 4 meters per second. It then runs into and compresses a spring until the package momentarily stops. Its path to the initially relaxed spring is frictionless. So the blue tabletop there is frictionless. But as it compresses the spring, the kinetic frictional force from the floor of magnitude 20 newtons acts on the package. So we're telling you the force of friction. We could have given you mu, and mu Fn would have given you the force of friction, but we're just giving you the force of friction is 20 newtons. If the spring constant is known to be 1,000 newtons, by what distance d is the spring compressed when the package stops? So we have, I'm writing in red, let's write in black. So we have 2 kilograms, we have a speed of 4 meters per second. We have a K value of 1,000 newtons per meter. The way you can physically think of the K value is, it's got units Newton per meter, and that means you need to put in 1,000 newtons of force to elongate or compress the spring by 1 meter. That's how you can think of the spring constant. We know that there's a frictional force of 20 newtons, and we want to know how far in the box will go. Now, this is a forces question, and I've always said before, free body diagram, F net equals ma. So let's do that, and let's see where we get stuck to properly illustrate kind of why we need energy. So if we start with a free body diagram, the moment the package hits the spring, then there's going to be a force backwards from the spring, and there's also the box is physically moving to the left, which means there's going to be a frictional force to the right. And I mean, of course, there's always gravity, and there's always a normal force. It just so happens that we probably will not need gravity or normal force, but we can still write them in. And my advice to you in the past is, after free body diagram, to do F net equals ma. So let's do F net in the x direction equals ma in the x direction. And looking at my free body diagram, what forces are in the x direction? Well, I've got the spring force in the x direction, and I have, let's let right be positive. So it's a spring force plus the force of friction. There we go. And this equals the mass of the box times the acceleration in the x direction. So the spring force, we know from Hooke's law, is kx, and friction is 20 newtons. So the acceleration of the box is going to be kx plus 20 over m. Usually, we would calculate the acceleration of the box and then put it into a kinematics equation and solve for displacement, right? If we know that there's a certain acceleration of an object, or I guess in this case, a deceleration of the object, and it has an initial speed, we know eventually it will come to rest. And using kinematics, we can find what this displacement would be. However, you'll notice that in my expression for acceleration, it's a function of position, which means as the box moves forward, its position will obviously change. And this means it's a non-constant acceleration. Non-constant acceleration. So this means we actually are not able to go any further, at least not at your level. You know, when you take senior physics, like second and third year, I think third year physics is when, at least at UTM, is when you take a classical mechanics class and you start learning how to sort of integrate these equations of motion. And then in fourth year physics, you really delve really, really deep into setting up F net equals ma and integrating to find your resulting equations of motion. Brandon can tell you a little bit about that. He just finished a class on classical electrodynamics, and you do a lot of that in that class. So at least presently, we do not have the ability to use Newton's second law to go any further. So this tells me that we actually have to try a different approach. This is exactly where energy comes in. So we say, we need a different approach. And, well, let me add some space. And I think we actually need a little bit more space. Okay. So now we can try energy, because the energy was really the reason we developed this. It's to accommodate non-constant accelerations. So we can say I'm sort of touching on something we'll talk about later, but the total energy before has to be the total energy after. And what I'm using here is I'm using the conservation of energy, which we have not officially talked about yet. I chose this question to really show you in a very concrete way why Newton's second law wouldn't work. And I didn't want to leave you high and dry. So I'm just going to use, very quickly, I'm going to use conservation of energy, but we'll talk about it in depth a little bit later on. But the main idea about conservation of energy is energy is not created or destroyed. So however much energy exists before an event has to be the same amount of energy that exists after an event. So before the package hits the spring, before it starts rubbing on the friction, we know that the total amount of energy is kinetic energy. This thing is moving, 1/2 mv squared. We talked about that yesterday. And then after, when the box is compressed, or the spring is compressed and the box comes to rest, then there's going to be a lot of spring energy, and the friction, there'll be a lot of work done due to friction. So you can feel like when you rub your hands together, they get really hot. The heat that you're feeling is the energy dissipated due to the force of friction. And I've said this before, physics is actually really cool. You can touch and feel physics. If you want to feel the work done due to friction, literally just rub your hands together. When they get warm, you are literally feeling and experiencing FD, force of friction times displacement. Okay, so setting this up, we're going to have 1/2 mv squared on the left, and then on the right, we're going to have 1/2 k x squared plus the force of friction, or the work done due to the friction is going to be the force of friction times the displacement. And I think we have everything here. We have m, right? M is 2 kilograms. Yep, so we have m. So check mark on m. Speed, do we have speed? Yeah, it's 4 meters per second, so check mark on speed. K, yep, 1,000. X, we're looking for X, we're looking for the displacement. Force of friction, yes, it's 20 newtons. So the only variable is X. One equation, one unknown. Solve. And in this case, you would need the quadratic equation. I don't want to actually go through the motions. The point of this question was not to bog you down with the quadratic equation. The point of this question, quite frankly, was to show students that absolutely, when in doubt, when you're facing a new problem, stick to things that you know. This is a forces question, sort of, so start with a free body diagram. Then go to F net equals ma, absolutely. Then you'll quickly realize that your acceleration isn't constant. And that is the trigger for new students who are still practicing and becoming comfortable with material. That's the trigger for students to figure out that you actually need energy. Now, our hope is as you do more practice with textbook questions, your brain will be able to sort of identify when you need energy ahead of time. Because I agree, doing a free body diagram and doing F net equals ma when you don't need to is time consuming and tedious. So, you know, hopefully I hope students will get to a point when you don't have to do that to realize you need energy. You know, practice makes perfect, but if you are still practicing and becoming comfortable with the material because you're new, then that's totally understandable. I'm giving you a framework that you can use to help identify when to use energy. So yeah, while you're new, I would strongly recommend always sticking with a free body diagram, F net equals ma. And in the event that a is not a value, like it's a function of x, that's what gives you the sort of flag to go to energy. Okay, moving on. Yeah, there was that quadratic equation I was talking about. So we'll talk about conservation of energy in more detail later. Let's move on to another scenario in which we do not have constant, where we do not have a constant force. When we were studying circular motion, we were doing a lot of, well, there's two types. There's horizontal loops and there was vertical loops. And horizontal loops were relatively easy, but vertical loops, we had to make a sort of an assumption that when we had something going in a vertical loop, we still had to say it was a uniform circular motion vertical loop, meaning as the object is traveling in a vertical circle, it was traveling at the same speed, which in real life is very difficult to do. We know from our analysis and our basic intuition that, you know, if an object has a certain speed down at the bottom, if you were to throw the object up in the air, it slows down as it rises, right? Because gravity's pulling down. So just because you're traveling in a vertical circle, like picture a roller coaster doing a vertical loop-de-loop. You know, the roller coaster at the bottom has a certain speed, and as the roller coaster rises, it's going to slow down. Like there's inherently a maximum radius of vertical loop that the roller coaster is able to take. I mean, if the loop is too tall, it'll never make it over the loop. So clearly, in real life, vertical circular motion, the speed will change. And we were not able to previously account for this because it would be a changing force, because, you know, a changing velocity would mean that our centripetal acceleration, oh, I'm still in pointer mode. A changing velocity would mean that our centripetal acceleration changes. And if our centripetal acceleration changes, then our net force would change as well. So previously, we were not able to handle non-uniform circular motion. And energy allows us to sidestep the problem. And I'd like to say it's like a Band-Aid, but it's better than a Band-Aid. It's like a permanent solution. Like energy is a very elegant idea. So let's kind of show you how we would use energy ideas for, is that the answer? Yeah, that's the answer. Let's see how we would use energy ideas to help solve this type of scenario. Again, we're gonna need to piggyback on conservation of energy, but I just want to outline for you, kind of like what I did before. I want to outline for you why there's a problem, and I'll quickly solve it, but we'll come back to conservation of energy later. So a small block of mass m slides along the frictionless loop-the-loop track shown below. If the block starts at point P, determine an expression or a formula for the net force acting on it at point Q. So you'll notice that, I don't know what happened. You'll notice, oh, that got smaller for some reason. The block on point P, as it slides here, gravity is pulling straight down and the normal force is pointing straight out that way. But as it falls, let's say it's here now. Oh, what's happening? As it's here, gravity's still pointing straight down, but the normal force is on a different angle. So as it falls, the net force on that P block is changing. There's a component of gravity pulling it forward, and it's different as it progresses. So there's a changing force. So figuring out how fast the block is going at the bottom, or even how fast the block is going at point Q, is going to be difficult using kinematics and dynamics, because the force is changing on block P as it's coming down this track. So we can go to energy, and we can do similar things with energy. We can say, oh, I'm still on pointer mode. We can say that the total energy before, meaning at point P, has to be the same amount of energy at point Q. And they're asking you for what is the resultant force acting at point Q? Well, we know that F net at point Q, it's supposed to be a Q, is going to be MAC, centripetal acceleration, because we can see there it's going to be a circle. And this is going to be mv squared over r. So pretty much we have r, we have m, we just need v. So the amount of energy before is going to be gravitational potential energy, which, before I get a bunch of questions in the chat, I know we haven't talked about gravitational potential energy yet. I'm just trying to show you kind of another scenario in which we have a variable force. So please bear with me. We have gravitational potential energy and no motion. We've got no kinetic energy ahead of time. And then after the fact, at point Q, what kinds of energy do we have? Well, we have a little bit of altitude left. So we have a little bit of gravitational potential energy left. And we also have kinetic energy. And kinetic energy, as you know, is going to be 1/2 mv squared. So we can actually solve for v squared. And plug v squared into our F net equals mv squared over r equation. Now, I'm not doing that presently because I have not yet explained and taught what gravitational potential energy is. So at this point in time, we're not supposed to know what the formula for EG is. But I wanted to outline for you the logic we know so far, and the logic is possible, okay? The exact equation, the exact solution is there for you. We can come back to it later once we've covered conservation of energy and other types of energy like gravitational. The last type of variable force I want to present to you that we're going to deal with this in class is gravity. Now, we know that gravity near the Earth's surface is mg, and this is constant. However, we learned, I think last Wednesday, a week ago actually today, that Newton has a law of gravity, and that's more of a generic equation. It governs the force of gravity between any two objects, whether it be you know, myself and my table, or whether it be the moon and the earth. Newton's law of gravity literally says that as long as the objects have mass, they will exert a gravitational force on surrounding objects. And I think we did an example last week where to explain why we don't notice the force of gravity between, let's say, myself and my phone. You know, I can't just hold my hand out and then have my phone kind of like come to my hand because gravity is attracting it. We did a calculation last week that showed that the order of magnitude was like really, really small. We're talking like, I think 10 to the minus 6 newtons or something like that. Nowhere close to enough amount of force to pull the object toward my hand. Although, I don't know, I'm just thinking about Star Wars now. You know, when they have the force and they can do this and make things fly at them. Maybe what they're doing is maybe they have a way to like bend the space-time continuum so they can like warp gravity, and they can change how much gravitational force something has on an object. I'm just trying to apply physics to a made-up situation. Anyway, that's what we do half the time as well. We kind of daydream about things that don't matter. Okay, back to this. We know the force of gravity, Newton's law of gravity, that is G m1 m2 over r squared. And generically, we know that to get the associated energy, we take the integral. So, you know, if you integrate, G and M are constant. So, you know, to get energy, gravitational energy, you take the integral of the gravitational force. And I'm kind of being a little bit, I'm abusing the math a little bit. I'm not showing all my detailed steps, so please don't barf all over my lack of math detail. Fg is gm1, m2. Those are all constants, so I can pull those out of the integral. So really, I'm integrating 1 over x squared, and that's going to be minus 1 over x. So that's where this equation comes from, right? It's just the integral of Newton's law of gravity. Again, we've done lots of examples where you would, you know, not have a constant gravity. Primarily, I guess I would sum that up by saying not near the Earth's surface. So most of what our day-to-day lives, most humans would experience, gravity is constant, right? It's just force of gravity equals mg. However, when we're analyzing things that are not near the Earth's surface, you do have to sort of take into account that gravity is a variable as you go from the Earth's surface up really tall. So things like celestial satellites, whether it be the moon is technically a celestial satellite, or a man-made satellite like a rocket ship or the International Space Station, they have a different amount of gravity up there. So if you are traversing a long distance where the force of gravity would change over that distance, you in fact have to use energy ideas instead of dynamics, with force of gravity being mg. Okay, this leads us to potential energy. And we sort of just use this with the block from point P to point Q and all this other stuff. So let's kind of explain where this comes from. So we do know that the work equals to the integral of force times displacement. We just now finished talking about what happens if the law of gravity, Newton's law of gravity, needs to be integrated specifically because we're over such a long distance and the motion is happening over such a long distance that the force of gravity changes over this distance. Then you need to use the previous equation. However, near the Earth's surface, we know that the force of gravity is mg. Now, as a side note, do you remember what g equals? I told you, I think a week ago, that you can actually calculate 9.81. It's not just something you can derive. You can also derive it in a lab, but it's not something that's only derived in a lab. You can theoretically calculate this value. And just as a reminder, it's capital G, mass of the Earth, over radius of the Earth squared. If you Google all those quantities and multiply them and divide them as per that equation, you should end up getting 9.8, which is kind of cool. Anyway, near the Earth's surface, if we assume the force of gravity is constant, then this is going to be the integral of mg dx, which is, oh, I should, okay, let's say x1 to x2, x1 to x2. M and g are constant, so we're integrating x, we're integrating dx between x1 and x2. And this is going to be mgx between x1 and x2. I don't know why. Every time I'm near the bottom of the screen, the pen goes all wiggly. That's not me. If I was able to do that so precisely, that would be a talent. I definitely cannot take credit for that. So this is just mg, x2 minus x1 is, say, delta x. Or some textbooks will call this the change in height. So that's what this equation here is saying. You have a certain amount of energy that's associated with the force of gravity. In fact, I can generalize this idea and say every natural force that exists, natural force, not me pushing on an object, but a natural force like the force of gravity, the spring force, for instance, every natural force of gravity that exists if humans were to just cease to exist. I don't know what happened there. that was weird. My tablet literally just turned off. Okay, am I still recording? I don't know. Welcome to the worlds of technology. Someone says, yes, I'm still recording. Okay, I'm gonna trust that I'm still recording. I hope this works out. I don't know. My tablet literally just turned off, so I have no idea what's going on there. Let me share that screen again. Okay, so, all right, let's just resume. Every natural force will have an associated energy with it. So we've calculated the associated energy for the spring force. That was 1/2 kx squared. We calculated the associated energy for celestial gravity, like gravity that happens over a long distance. And we also calculated, just now, we calculated the associated energy with gravity near the Earth's surface. That's just mg delta h, meaning it's not a function of position, or sorry, it's not a function of path traveled. It's just a function of where the object ended up versus where it started. So it doesn't matter if the ball, I don't know why a ball would do this, but like, let's say the ball started from the ground and somehow was elevated to height h in this sort of squiggly pattern. All that matters, just because you went into a squiggly pattern doesn't mean more energy, more potential energy went into the ball. The formula, the math, they just say the gravitational energy of the ball is only a function of altitude off the ground, not the path by which it achieved that altitude. And this is actually more concisely summed up in the next chapter. So if you're looking at the typed notes now, we'd be in chapter 7 or section 7. It's this notion of a conservative force versus a non-conservative force. And a conservative force, most things I would say that you're going to experience in this class are conservative force. A conservative force means that the amount of energy associated with that force is not a function of path. So, you know, like I just said with gravity, if you have a ball and you take the ball and for some reason you make the ball kind of go up on a weird angle or in a weird zigzag path. In fact, there's a street in San Francisco called Lombard Street. Very famous, very, very, very famous street. It's like that zigzag street that's in all the movies in San Francisco. That is exactly what I'm talking about. If you want to measure the change in gravitational potential energy of a car at the bottom of Lombard Street versus the top of Lombard Street, all you're doing is you're measuring the altitude difference. And the fact that the car traveled a long distance, right? I mean, they're having to travel. Look at all this extra distance they're having to travel. They're having to travel all this extra distance here. Of course, it would be very much shorter distance to travel vertically upwards. Of course it would. But whether you travel vertically straight up or whether you travel up on a zigzag does not change the amount of gravitational potential energy that the car has obtained by driving up Lombard Street. That is what is meant by a conservative force. Another example of what I mean by a conservative force. If you have a spring, that's a terrible spring. If you have a spring and, you know, let's say I'm going to change colors here for a second. If you compress it and you uncompress it a little bit and then you compress it a lot and you want to know how much spring energy it has, you know, let's say this is step 1, we compress it a little bit. Step 2, we uncompress it a little bit. And then there's that pen being weird again. Step 3, we compress it a lot. Let's say we want to know how much spring energy is stored in our system. All we care about is, because the spring force is also conservative, all we care about is 1/2 k x squared. What is the net elongation of the spring? Here the elongation was 0, and here the elongation was not 0. So it doesn't matter that I took 2, 3, 4, 10, 100, a million intermediate steps. If you want to know how much energy a spring has, all you have to do is know what the elongation currently of the spring is. Now, I guess it might be better to explain what a conservative force is by explaining what it's not. That might give you a better context of what a conservative force is. What is not a conservative force is, say, friction. So let me add, I don't know why it does that. Let's try it again. Insert. Okay. So what is not a conservative force? And what's not a conservative force, as I said before, is friction. And this is because the energy, or I should say the work done, is a function of path. What do I mean by that? Picture this. If you take a box, and you drag a box this way, so the box is now here, then you will have some sort of work done due to friction. So the work done due to friction would be the force of friction times the displacement, where this would be, say, d. However, if I were to move, let me add some space again. If I were to move this box back, I'm going to change it to green now. If I were to move this box back, let's say halfway to where, halfway back home, halfway to where it initially started, then the work done due to friction would not simply equal the force of friction times half the displacement. Because as you're rubbing, as the box is being dragged across a rough surface, for every centimeter that the box is carried forward over a rough surface, there is energy being lost due to heat. And you can feel this. If you rub your hands back and forth, the net displacement of your hands, hopefully, is close to 0. Hopefully the displacement of your hands aren't kind of like way off in no man's land. But if you go back and forth, back and forth, back and forth, back and forth, you're constantly going, you know, farther away and then towards. So your displacement is 0, yet your hands are warm, meaning energy has been, or heat has been generated through friction. So in this case, the work done due to friction, you kind of have to break it down into multiple steps. You have to say it's the force of friction times the initial displacement. This would be step 1. And then it's the force of friction times, actually, you know what? Just for to match the drawing here, I should draw the first term in black because that was associated with black ink with this motion, and then green ink, force of friction times d over 2, and that would be moving back home half the distance. So it's not, when you move towards home with friction, you're not gaining back. You're not restoring that energy. You're continuing to lose more energy. With friction, every step you take, you're constantly spending money. A conservative vector would be, you know, whatever you buy, you can return. It's like Amazon has a really good return policy. So, you know, presumably you could buy something from Amazon, use it for 30 days and return it. That would be a conservative vector, something that you can get your money back completely if you need to. Friction is not a conservative vector. You know, every step you take, you're spending money. So things like food, presumably, you know, people need to eat every day. So every day you're spending money on food. And once you eat the food, you can't return it. So eating, I would say, is a non-conservative vector because you can't return it. So here's a conceptual example for us to sort of wrap our head around. I've been doing a lot of talking, and I think we're doing, well, we do actually, we're not doing terribly good on time. We have some examples to do. So I think I'm just going to talk you through this and we won't do an actual poll. Paul and Corinne start from rest at the same time on a frictionless water slide with different shapes. At the bottom, whose velocity is larger? So for instance, let's say we had one water slide that looks like this. And let's say we had a rather boring water slide that looks like this. Different shapes, that's all the question says. But we do know that they have the same altitude, okay? Question is, which one has a larger velocity at the bottom? And we have to ask ourselves, well, what type of energy are we comparing here? And the energy before is gravitational potential energy because they're elevated off of the ground. So the amount of energy this guy has is mgh. The amount of energy, that would be Paul, Corinne also has mgh. So they have the same amount of energy, sort of. They might have different masses, that's true. The question is comparing their velocity at the bottom. And their velocity at the bottom, though, we know that gravitational potential energy is a conservative type of energy. So we can convert without losing anything. We don't have a transaction fee, you know, we don't have a surcharge. We're assuming it's a frictionless water slide. So it really doesn't matter what path they take to get down to the bottom. Down at the bottom, the amount of kinetic energy is going to be the amount of gravitational potential energy they had at the top. So they're actually going to have the same because they're asking you to compare velocities. We know the kinetic energy is 1/2 mv squared, so equals mgh. 1/2 mv squared equals mgh. So even though Corinne and Paul may have different masses, the mass of the person cancels. So you see that the final velocity at the bottom of the slide is in fact not a function of the person's mass at all. So Corinne and Paul are going to have the same velocity. And that's what that says there. Okay, we're kind of on the last topic of new information. I'm going to see if I can play for you a link or sorry, a fun little video to orchestrate or to illustrate conservation of energy for you. The very last thing we need to tie everything together is the law of conservation of energy. And I've mentioned this kind of earlier on in the recording, but we have this notion in physics. Actually, it's a very, very, very fundamental law of nature, that you have this conservation of energy rule where energy cannot be created or destroyed, which means however much energy is present in a system ahead of time, a bunch of things can happen. You know, you can trigger a domino effect, things can fall, things can roll, things can break, blah, blah, blah. You can have friction, you can have heat loss, things can get transformed into sound. You know, all these things can happen, but at the end of the day, you cannot get more energy out than what you put in. So there's this idea, maybe from high school, you know this, there's something called a Rube Goldberg machine. And, you know, it's pretty much a lot of things that a lot of elementary school teachers and high school teachers like students to build, because it shows how energy can flow and transform between one form of energy and another form of energy, how energy can be converted between potential energy and kinetic energy, or, you know, vice versa. So let's have a look at this. I'm gonna share YouTube for a second. There's YouTube there. Okay. YouTube. Actually, I wonder if I just click the link. Is that a thing? Of course that's not a thing. Okay, we're back. I hope you enjoyed the video. I understand that the recording and the internet may still have a bit of a lag, so maybe the video did not come across as well as I would have wanted. But you can watch the video yourself. I gave you the title here. It's called "Okay Go Rube Goldberg." So if you search that on YouTube, you could rewatch the video on your own. Um, I'm also trying to record, as I said earlier, locally on my computer, which means even if Zoom is a little bit slow with the lag, hopefully when I post a recording on YouTube, there is no lag. That's a bit of an experiment we're going to try this time. Anyway, a bit of a debrief now that you've kind of seen what a Rube Goldberg machine is. He's the group of them, I think there was like 5 or 4 of them. He started it with just a nudge of a little toy pickup truck, which is what you see here on the lecture slide. And if you want to think of kind of the initial premise of what I was saying, the energy that you put into the system is constant. So the energy that the person puts into the system is just a little bit of kinetic energy, right? Just a little bit of a nudge from a toy car. And this little bit of energy is able to move a piano, break a TV, you know, have bowling balls rolling everywhere, and, you know, balloons falling. Like, it seems disproportionate. Which is the point. It's supposed to be a thought-provoking video where it seems like you only put in a small amount of energy and all these big things happen that couldn't possibly all equal the same amount of summed up energy as what was put in the system. So really the question is like, what is going on? And you have this notion, this video illustrates that you have this notion of stored energy, that the amount of energy in a system is not just what you kick the system with, right? This person kicked the system with a tiny dinky little car, and yeah, that did add a little bit of energy to the system. Yes, it did. You know, 1/2 mv squared. It's a small m because it's a small toy car, and it was traveling pretty slow, so it's a small v squared. Okay. Yes, it added a technically non-zero amount of energy to the system. However, there's a lot of stored energy in the system. And we've talked about the previous forms of energy just above this. We talked about spring energy. You can store, you can compress a spring and then lock it in place. Well, your muscles are the ones compressing that spring. So you're putting energy into the spring. You've done work on the spring, and you've maybe put a lock on it, and you've stored that energy to be used at a later time. And you can release that energy as you wish, you know, at your whim. And you can lift objects up and suspend them in the air, which is with a Rube Goldberg machine. A lot of the times that's what they do. They had objects on a ramp at the top of a table, and they fell down maybe in a circular way down the ramp. So you're putting gravitational potential energy stored within the system. So all it takes is a little bit of a nudge. You know, all you need to do is kind of like hit the bowling ball, and then if it rolls forwards, it might roll off of the table. And then as it rolls off of the table, it takes its gravitational potential energy and it converts it into kinetic, and it can cause some other chain reactions. So this video is a really good illustration that of really conservation of energy, and how energy can flow between different forms. It can flow between gravitational to kinetic, spring to kinetic, gravitational. Kinetic can roll something up a hill, and as it rolls up the hill, it slows down, so it's converting kinetic back into gravitational potential energy. So that's really the heart and the main concept of conservation of energy. And you know, we can talk about the math until the cows come home, but really, at the end of the day, what conservation of energy is quite simple. Really, what conservation of energy is the amount of energy before an event. Oh boy, that's a terrible underline. The amount of energy before an event has to equal the amount of energy after the event. So the energy before has to equal the energy after an event. Now, up until this point, we've really only learned like 3, maybe 4 types of energy, right? We've learned gravitational potential energy. So, you know, if you're trying to say energy before equals energy after, you're comparing, well, how much gravitational potential energy does the object have before versus how much gravitational potential energy does the object have after. So that's what EG and EG prime is. EG prime is not a derivative, but rather meaning after the event. The other type of energy we've learned is spring energy, 1/2 kx squared. So you can say, well, how much energy does the spring have before the event, and how much spring energy does it have after the event? And same thing with kinetic, how much kinetic energy does it have before an event, and how much kinetic energy does it have prime after the event? The only thing that I haven't quantified is work NC. Work NC means the work done to the non-conservative forces. I'm sorry, my handwriting is messy toward the bottom of the screen. What this means is work that you either put into the system, like let's say you're pushing your sibling on a swing, which please don't go to the park now during COVID, that's bad. But maybe think about if you have a sibling, a younger sibling sitting on a swing, what is their energy at the moment? It's zero, right? They're not moving, you know, they're not kind of up here on the swing, they're just kind of sitting stationary down on the swing. And what you do is you come in and you push them. Well, you pushing them, you're doing work on the system and you're putting energy into your sibling on the swing. And that is a non-conservative force, right? The force from your muscles and your arms when you push, you can't get that back. You know, you can't take that energy and put it back in your muscles. Once you've used it, you've used it. So that's what I mean by a non-conservative force, or work done due to a non-conservative force. And you can either have the work done on the left-hand side of conservation of energy, or you can have the work done by a non-conservative force on the right-hand side of conservation of energy. It really depends whether the non-conservative force is putting work into the system or taking energy out of the system. So, you know, you pushing your sibling on the swing, you're making them go faster, traveling higher and higher and higher. I would say pushing someone on a swing, it's payday. You're putting money in the bank account, you're putting energy into the system. A type of force that takes energy out of the system would be friction. You know, every time an object moves forwards, you're losing energy due to heat. So the work done due to friction would often show up on the right-hand side because it's taking energy out of the system. You know, you get paid, but then you have to buy food, you know. Okay, so in terms of content, that's pretty much all there is. I specifically chose to take power out of the lecture slides just because we didn't have, I knew ahead of time we were not going to have time to cover power. There's really not a lot to power. Very, very briefly, I'm going to mention that power is the rate at which energy is dissipated. It is the derivative of the work done with respect to time. So, you know, if you want to lift a fridge from the ground floor up to the first floor, you know, that's a certain change in gravitational potential energy, right? A certain amount of joules required. But if you lift the fridge up really, really quickly, you're going to be tired and panting and hopefully you don't have a heart attack. But it's going to be hard to lift the fridge up really, really quick up those stairs because your power consumption is high. You're trying to change the gravitational potential energy over a short period of time. Whereas if you lift this heavy object like the fridge, one stair at a time, you take a break, lift it one stair at a time, take a break, you are changing the energy by the same amount of joules overall, but you're doing it over a longer period of time. So you are consuming less power. That's all power is. It's just the rate of energy consumption per unit time. There's a little bit more details in the typed notes. So I would encourage students to go look at the typed notes. I think it's at the last page of the typed notes. So they're there. Okay, that's all the knowledge. Now we can just go through and just do some practice problems. Everything is in place to just kind of hammer through some practice problems. So without further ado, let's just go nuts. So we are going to find the minimum speed required to complete the loop-de-loop. We'll do this via an energy argument. For ease, we'll ignore friction because that's what physicists do. We pretend like friction doesn't exist half the time. So we have an object, say, that is coming in and is traveling here and it enters the loop, and it travels around, and then it exits. And I'm sure you can imagine, just like literally picture this in real life. If the object is coming in very slowly, then the object might get here and then stop and then roll backwards, right? If there's not enough speed or energy coming into the loop, there's no guarantee that it'll make it all the way around. You can obviously be going too fast for the loop. If you go too fast for the loop, the loop will just pull you in and blah, 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 blah. But if there's a too slow and good enough, there has to be a speed at which there's a perfect speed that can bring you around the loop. So let's see if we can figure out how to do that one. So we are going to find the minimum speed that you require to complete the loop. We'll find this via an energy argument. So this says, here the key is that the minimum speed happens when the normal force at the top is equal to 0. Now, why is this the case? Here I am at the front of the class, quote unquote front of the class, telling you this condition. But if you had to think about this on your own, how would you come to this conclusion on your own? If you're traveling too fast for the loop, then at the top of the loop, you need a force from the track pushing you inwards to help keep you traveling along this path. So if you're traveling too fast, you're going to have a normal force pushing down on you at the top. And if you're traveling too slow, you'll just fall right off of the loop completely, and you won't even have a normal force, let alone in contact with the loop at all. So naturally, the sweet spot, the speed at which you can perfectly go around the loop without the loop having to keep you there, would be when the speed at which right when the normal force stops acting. And if had you been going a little bit further, the normal force would have to pull you in, and if you were going too slow, you would just fall. So the sweet spot there is when the normal force is equal to 0 at the top. So if we compute that, we say this is going to be the force of gravity acting down for my free body diagram, and there's nothing else. We are of the assumption that we are solving for a speed that results in no normal force. So that's the only force in my free body diagram is gravity. And from this, we use F net equals ma, and we're told in the question that it's a loop-de-loop. So we know that this is mac, and we're going to get mv squared over r equals mg, because the net force is just gravity. So here we see that the minimum speed at the top of the loop is going to be the square root of rg. So that is the speed at the top of the loop that will allow us to maintain circular motion, but not need a normal force at the top to help maintain circular motion. The only force contributing to circular motion in this scenario is gravity. Now that we have a speed at the top, we want to find the minimum speed. I guess at the top of the loop. Well, I guess we did that. So here, find the minimum speed required to complete the loop-to-loop. I'm giving you a hint. First, calculate the minimum speed at the top. We want to calculate what the speed is when you enter the loop. So we can reverse engineer. We can say, like, let's say there's a stunt guy on a motorbike, and he's trying to drive his motorbike around the loop. If he's looking at the speed on his motorbike as he enters the loop, what speed does he need to enter the loop at the bottom so he achieves this minimum speed at the top? So here we can use energy. Energy total, I should say energy bottom, has to equal energy total at the top. Well, at the bottom of the loop, what forms of energy does he have? Well, let's look at the conservation of energy equation. Let me just erase all of these markings to make it easier for you. At the bottom of the loop, does the guy, actually, you know what, let's just write out this equation here. We'll just write out the whole thing. Come on, insert space. So we have gravitational energy before, spring energy before, kinetic energy before, gravitational energy after, kinetic energy after, spring energy after. So I'm writing out, also the work done due to friction. So this is the complete conservation of energy equation to date. As the course progresses, we'll be adding terms to this. But right now, these are the only forms of energy we have. So let's ask ourselves, what kind of energy does this object have at the bottom? Well, there is no spring at all. So he's got 0 spring energy. And he is on the floor. So he does not have any altitude. So he does not have gravitational potential energy at all. Okay, at the top of the loop, is there a spring? Nope. There's no spring anywhere in the question. So I can cross that off. Is there friction anywhere along the path? No, we assumed it was frictionless, so we can cross friction off. Is there gravitational potential energy? Yes. This object has a height off of the ground, so we have to keep Eg prime. And is there kinetic energy? Yes. We know that this thing is moving at the top of the loop. So there's going to be some kinetic energy at the top as well. So I think this is our conservation of energy equation for this situation. It's going to be Ek at the bottom equals gravitational at the top plus kinetic at the top, which means we're going to get 1/2 m v bottom squared equals gravitational potential energy. That's going to be mg delta h plus 1/2 m v at the top squared. Okay, what do we have and what do we need? I'm getting lost in the question here. So we have radius. So the height of this object is going to be twice the radius. So we have delta h. G is a constant, obviously, so that's fine. We have v at the top. So that's a check mark. M, we don't have m, but luckily m cancels. So the only thing we need is v at the bottom. All right, so let's just rearrange. Now that I know kind of what's going on, let's rearrange here. So solving for v bottom, we're going to have v bottom squared equals g times 2r. So the change in height is twice the radius. Oh, I'm bringing up the 2. So 2 times plus 2 times 1/2 times v top squared. So this is going to be the speed at the top, so it's going to be root rg. Oh, the pen is doing something weird again. So it's going to be root rg squared. And that means my speed at the bottom is going to be the square root of 4 rg plus rg, which equals the square root of 5 rg. So there you go. That's the speed at which the object has to be traveling at the bottom of the loop in order to make it to the top of the loop and then continue the circular motion without falling straight down. Now, I've mentioned this before. Please, please, please try to have a final derived equation. Not only is it good practice and you're going to get more marks for having your final derived equation versus plugging in numbers early, This helps students answer questions like, what if I say, if I double the radius of the loop, by what factor does the required speed at the bottom change? And here you can see, if I double the speed of the loop, sorry, not double, if I double the radius of the loop, if I double r, I only need to increase my speed by √2. I don't need to double my speed. I only need to like increase my speed by 40% because √2 is like 1.4. So it's really good to have a final derived equation because then you can see how the variables relate to one another. Okay, we might go a little bit over time, but this is a really important question, I think, to help illustrate energy. And it kind of hits close to home, actually. I don't know if many of you spend a lot of time in the Davis building. If you're not from our campus at all, most of you are from St. George or Scarborough, so you will have no idea what I'm talking about. But the Davis building used to be called South Building. And South Building is the second building built on our campus. We used to have something called North Building, which was the first building built on our campus. And it had been since torn down and something else has been built in its place. But South Building has been renamed to the Davis Building because some old politician donated a bunch of money to have his name put on the building. Anyway, point being, it's an old building. And the elevators in this building are, we'll say, sketchy, to say the least. I'm sure they're well maintained and I'm sure they're safe, but you know, when the elevators go up and down, you hear screeching and, you know, it kind of oscillates back and forth. If you're nervous with elevators, I would recommend not traveling on those elevators. So this question is to sort of reassure people about the safety mechanisms of an elevator, specifically the ones in Davis, but, you know, it's a fun physics question nonetheless, and it happens to hit home for the people who are from UTM. So here's an example. The cable of the 1,800 kilogram elevator cab in the figure snaps at some point, maybe because it's old, I don't know. And the cab is currently at rest. So maybe it's on the 5th floor of Davis and the elevator doors are open and they're moving some lab equipment. Maybe they have this big optics table, or maybe they have a giant trolley of liquid nitrogen or something. So they're loading a cab and they put too much weight in the cab. So it's stationary at first, but they just load it too heavy and then the cable snaps. That's kind of the situation here. When the cab is, let's see here, at rest, where the cab bottom is currently at a distance of 3.7 meters above the top of a spring. So the spring is underneath this, this really stiff spring is underneath this elevator to provide a bit of a cushion if the elevator were to break and fall freely. The spring has a spring constant of 0.15 meganewtons per meter. It's a very, very stiff spring. In addition to that, there are safety device clamps that push against the guide rails in the event of free fall. So like, you know, when you're turning, like let's say your car turns a corner and your seatbelt locks, there's a mechanism in your seatbelt that detects a certain type of acceleration. And if your acceleration of your car goes above a certain threshold, it locks the seatbelt using like a tilt mechanism. Same thing with brakes in an elevator. If it detects the acceleration of 9.8 or larger, the brakes flare outwards and provide some friction. Like I said, there's physics all over a car. It's not even funny. Okay. A, find the speed of the cab just before it hits the spring. Okay, there's a lot going on in this question, so I'm just going to write it down. Mass equals 1,800 kilograms. The distance between the cab and the spring is 3.7 meters. Spring constant is 0.15 meganewtons per meter. And there's a force of friction of 4.4 kilonewtons. And we want to find the speed at just before touching the spring. So we want to find the speed right here. So I'll tell you, I've said it before, I'll say it again, physicists and words do not mix very well. You know, or reading comprehension is probably, now, not that I've done a formal study on this, but I'm going to guess that a physicist's comprehension of reading is far below the average in terms of other disciplines, especially in the humanities. So we don't like words. So I've removed all the words from the word problem. Words are now no longer an issue. I've written down all my values. I've gotten a sense of kind of what's going on. I know there's an elevator that's falling, and I need to find the speed before impact, really is what's going on. So I could actually find, for part A, I could find this in two ways. If I wanted to, I could solve for this using dynamics. It's got a constant force, the force of friction, that's not changing with time. It's just a constant force, and gravity's pulling it down, which is also a constant force near the Earth's surface. So constant force means constant acceleration, which means if I really, really wanted to, I could use F net equals ma to solve for A, and then use kinematics to solve for V final. Or I can bypass all of that double step process, and even though I have a constant acceleration, I can still use energy, because energy, it's especially useful when you have a variable acceleration, but it's still useful and still applicable even if you have a constant acceleration. So let me show you how we would use energy. We would start with energy total before equals energy total after. Before, we have some options. We have spring, gravitational kinetic, and then afterwards we have gravitational prime, spring prime, kinetic prime, and the work done due to friction. Same start as what I did before, if you, recall how we started before. So I asked myself, before, is the elevator moving? No, it's not. So there's no kinetic energy before. Is there any spring compression before? No, it's not. Is there altitude before? Yes, there is. It's 3.7 meters above the ground. So I cannot cross that out. After the fact, well, after the fact, it's fallen the whole distance. So it's used up all of its gravitational potential energy. And has the spring started to be compressed yet? And if we reread part A, we say no, it says it's just before it hits the spring. So the spring hasn't been compressed yet. Will the object be moving? Yes. So we cannot cross out kinetic energy. And has there been friction taking energy out of the system as it falls? Yes. So we have to keep work done due to friction there. So this, I think, gives us our starting equation. We see that gravitational potential energy, gravity can transform into kinetic energy at the bottom, plus the work done due to friction. So this is going to be mgh equals 1/2 mv squared plus the force of friction times displacement. Or I guess the displacement in this case is the height that falls. And there you go, there's your equation. What do we have and what do we need? It says V final. So we're looking for V final. Do we have mass? Yes, we do. Mass. Do we have height? Yes, we do. It's the distance that it's fallen, 3.7 meters. So we have height. Do we have friction? Yes, it's 4.4. And G we have. Okay, so we have everything except V. So let's go ahead and solve for V. So let's see here, 1/2 mv squared is going to equal to mg. I'm going to change h to d just because I have d here written in my variables. So d minus force of friction d. And that means my v is going to be mg, oh, sorry, it's going to be gd minus force of friction d over m times 2 times 2 all square rooted. And there you go. So there's a formula for the speed of the elevator just before it strikes the spring right there. And the last part of the question, I know we're a little bit over time, but we're not going to be too much longer, I promise. The last part of the question, this is the answer for part A. Part B says, find the maximum distance that the spring compresses. So we see here, let's just regain some context in the problem. The whole point of safety mechanisms in an elevator is that they prevent the elevator from crashing into the ground, right? So the brakes along the way help slow down the elevator, but if the elevator is still traveling at a non-zero velocity by the time it hits the spring, you don't want the elevator to just go whack right into the ground. That would kill everybody inside the elevator, or if not, seriously injure them. So the spring is there to provide a little bit of a cushion to decelerate the elevator further and to take more energy out of the system, to absorb the energy, to absorb the kinetic energy and transform it and store it into the spring. So we see here that when it strikes the spring, there is still a speed, which means the elevator is going to continue downward to compress the spring. And then as the spring gets compressed, it will steal some of the kinetic energy, and eventually there'll be no kinetic energy left, and the elevator will come to rest. So that's what part B is. Part B is find the compression of the spring in order to bring the cab to a complete stop. So here we say E total equals E total prime again. And we say, okay, what is the energy before? What is the energy after? Well, we can just write everything out. E spring plus E gravity plus E kinetic equals E gravity prime plus E spring prime plus E kinetic prime plus work done due to friction. Same start as we did before. Now keep in mind here, now we are here, so we are scenario A, and then down here is scenario B. Okay, so we're no longer looking kind of originally where it was suspended above the spring. E total before is at the top of the spring, and E total prime is after it compresses the spring. So just before it compresses the spring, what's the energy stored in the spring? 0. Does this object have gravitational potential energy? Well, in this case, it does, because the premise is that a little bit later on, after the object comes to rest, it will fall some more distance. So it does have gravitational potential energy still. And is it moving? Yes, it's still moving. Am I still on red? Yes, I'm still on red. Okay, what's the gravitational energy after it fully compresses the spring? Well, it will have come to rest, so 0. It has nowhere left to fall. Is there spring energy? Yes, because it will have compressed the spring. Is it still moving? No, so there's no kinetic energy left. And work done due to friction. I'd still say yes. As it falls, it's still rubbing against the rails. So as it falls, there's still friction. So there's our equation, and let's set it up here. We have EG, so that's going to be mg, what are they asking for? The compression x, the maximum distance x. So mg delta h is going to be the, well, let me just write mg delta h here, and we'll fix it later. Kinetic energy, 1/2 mv squared equals spring energy, 1/2 kx squared, and work done due to friction, force of friction times displacement. So there it is. What do we have? What do we need? Mass we have, delta H. Delta H, how much does this elevator fall as it compresses the spring? Well, it falls a distance of x. So let me just change this delta H to x. V squared we have the speed before impact from here. So this is going to be used in part B. Mass we have, K we have, X we're looking for, force of friction we have, and the distance traveled again is X. Okay, so where does that leave us? That leaves us with mgx plus 1/2 v squared. V squared is going to be 2gd minus 2fd over m equals 1/2 kx squared plus, is force of friction a number? Yeah, 4.4 kilonewtons, so I can just leave that as force of friction times x. All right, so that's a long equation, but I think we actually have everything. I think we have everything except x here. Let me just double check. Mass we have, gravity we have, x we don't have, mass we have, gravity we have. This d was the d from before. It was the 3.7 meters. Force of friction we have, 3.7 meters we have, mass we have, k we have, x we don't have, force of friction we have, x we don't have. So it looks like we only have one unknown. Now, yes, the unknown pops up in multiple places, but we only have one unknown, and that unknown is x. So here we actually have to solve the quadratic equation. So there's the answer to part A, which we got before, and then this is the solution to part B. This is the same setup that we had previously, and I've rearranged it for you on the lecture slide here to show everything on one side of the equation, and then you can just solve for your A. Well, you know that k, 1/2 k is going to be your A value. Your force of friction minus gravity is going to be your B value, and 1/2 mv squared is going to be your C value, and you can use that in the x equals negative b plus or minus b squared minus 4ac all over 2a quadratic equation. So you can use A, B, and C in that equation there. And you can solve for your compression, and then your maximum compression of the spring is going to be 0.9 meters. So there you go. That's how you do energy. Now, there's some examples we didn't have time to get to. This is from your textbook. It's question 40 from the energy chapter. So you can easily go and do that one on your own. And here's another fun one. I don't have solutions posted for this. If you look later, there's just no solutions there. So this one's just fun. I wanted you guys, just like with the pulley question, you know how I ended the dynamics chapter with a really, really fun pulley question? I'm ending this chapter with a really, really fun energy question. So you can try this one on your own. Before I let you go, and I know we're a little bit over time, before I let you go, I just kind of want to go back to the prelude for just a second. And I want to relook at these questions very quickly, just to sort of show your brain, as confused as you might be right now. I just want to show your brain kind of how much you've learned. So the first question here was, the second floor of a house is known to be 6 meters above the street level. How much work is required to lift a 30-kilogram fridge to the second story level? And does this amount of work change if the fridge has to be carried up a staircase versus hoisted up straight up a pulley? We know now that work is FD cos theta. So if it's hoisted straight up, the force is straight up and the displacement is straight up. So that would just be, 300 times G times 6 if it was straight up. However, if it was hoisted up along a staircase, then the force would still be upwards, but the motion would be diagonal along a staircase. So in that case, you'd have a theta value. So it all works out to be the same in the end, don't get me wrong. So the answer is no, it should not change the amount of work, but it's because you have to, part of your force is going to be lifting the fridge upwards, and then part of your force has to be pushing it into the, pushing it up the ramp. So you're going to have a higher force, but your cos theta is going to reduce the product. So it balances out. So the answer to part here is no. And then the answer to the first part is just 300 times 6 times G. So that one's fairly easy. Question 2, if we drop a banana off a house, calculate the velocity before impact. That one's fairly easy to do. You can do that with kinematics fairly easily. You know, V2 squared equals V1 squared plus 2GD. So assuming we knew how tall the house was, this would imply that the speed before impact was going to be the square root of 2G times, well, I'll say the height of the house. Okay, fairly easy. However, if we drop a banana from space and let it fall, is it still going to be root 2GH, where H is the altitude of the banana from space? Hopefully you know by now that answer is no, so it's not the same. When you're that far away, the force of gravity changes as the banana becomes closer. The force of gravity becomes stronger as the banana becomes closer to the Earth. So its acceleration will be larger as it falls, which means there's a non-constant force, which means we cannot use kinematics. So we use energy, and here we can say gravitational potential energy gets converted to kinetic energy, and the gravitational potential energy would be Newton's law of gravity, so Gm banana, m Earth over the height of the banana plus the radius of the Earth equals 1/2 m banana v squared. And then from here, you can simply solve for the speed of the banana. So that gets around that illustrates in a nice little concise answer why we use energy when we have a variable acceleration. And then lastly, I'll leave this one for you to think about. When driving, is it best to turn the car or is it best to slam on your brakes? This one, you will need to practice your problem solving skills. I don't really want to spoon feed you the answer to this one. This one's really fun to think about. And once you figure it out, I think you're going to be very proud of yourself. So anyway, I just wanted to compare your knowledge before and after. You know, you may have went into these lectures before being taught energy, not really knowing how to think of these questions, but as confusing as you may have felt over the past 2 lectures for energy, hopefully you are leaving these lectures with, you know, realizing you've learned something and that you're not expected to know intimately all of the energy ideas inside out and backwards walking out of the lecture, right? You do need to go home, you do need to practice to become more well-versed in these new ideas. But I just want you to leave the lecture kind of realizing you have learned something already, so keep at it and keep up the good work. Okay, I'll stop the recording shortly. Good luck on Saturday for your midterm. And after I stop the recording, I'll be happy to take some questions. Okay, see everyone on Monday, and good luck on Friday.